recording this lesson. Okay, guys, welcome. I'm glad to see all of you today. This is, what is this, week 12? We only have a month to go. We're going to be out of here. Summertime's right around the corner. Hope that you're hanging in there. I know it's a busy time, but hope everything is good. I was kind of off the grid for part of the weekend anyway, but I am back now, and I'll be around tonight, for example, for my office hours. And throughout the week, we've got a lot going on. There's actually 2 homeworks that are due this week. I did email you this morning, but just to kind of remind you about it, there's a homework assignment due tonight. I am going to see if you have any questions on it in a little while, probably after the break. I'll see if you want to talk about any of the questions from the homework. So we have that. There is also a homework that's due on Friday. You guys can already pretty much do that assignment. We've covered all of that material already, but just want you to know. So this week we do have 2 assignments, today as well as on Friday. Hopefully they won't be too bad. I think they're broken down pretty nicely as far as I can tell. Anybody have any questions about anything with logistics and whatnot? I hope I'm keeping my Canvas page up to date really well and trying to make sure that everybody's keeping up on everything. So far, so good. Okay, great. Well, let's get started here. I'm ready to jump in with you all. Actually, my recap for today is over here on the sideboard. I just want to remind you, what were we doing as of last Wednesday, right? We started finally, we started differential equations again. So chapter 8, and in fact, we only have 2 chapters left, chapter 8 and chapter 9. So we're just about into the home stretch here. We're going to use capital D as a derivative operator. So every time you see the capital D floating around, it just means take a derivative. You can see that right here, D of F equals F prime. If I have powers of D, right, if I see powers of D in my differential equation, that's just what I mean, take higher derivatives, second derivative, third derivative, and so on. The largest number of derivatives is this one right here, n derivatives. That's why it's called an nth order linear differential equation. This is the notation. Actually, look at this box. It's like so small. It's because this L is sort of compressing the notation down. So you're not really seeing a lot here. It's literally just L of Y equals big F. That's my nth order linear differential equation. The goal is to solve for Y. And hopefully today we're going to start to get some tips on how to do that part. You guys might have noticed we haven't really solved any differential equations since chapter 1. So I've got to give you some tips on how do we actually solve for Y. How do we accomplish our goal here? Turns out it can be pretty difficult. I mentioned this way back at the beginning of the semester, that even by the end of the semester, there will be lots of differential equations that we still don't know how to solve. But I do have some very good news for you. If you're an engineering student or a physics student, or really any kind of a science or math student, what you will soon realize, if you haven't already, is that most of the differential equations that show up in your applications, maybe it's electric circuits, maybe it's mechanics, maybe it's those, even a chemistry, those mixing problems we did, right? In many of those examples, and I was a physics major as well as a math major, and so I saw these with my own eyes, that many of those problems, yeah, there's differential equations to solve, but almost all of them are linear. Right? They're mostly linear, and a lot of them are actually homogeneous as well, which we'll talk about in a moment. So that although there are lots of differential equations that we will never learn how to solve, luckily the ones that we need to be able to solve for engineering and science applications tend to be the ones that we do have techniques for. those are the ones we learn how to solve. Okay, well, the first step to doing this, guys, the first step is going to be to solve the associated homogeneous differential equation. This word homogeneous is being used in a different meaning than when we saw that word in chapter 1. Remember the differential equations in chapter 1? We had what? Bernoulli and separable and homogeneous. And so there was a word homogeneous there. That's not the same meaning that I'm giving to the word homogeneous here. For the purposes right now, guys, in chapter 8, homogeneous just means this, that there is a 0 on the right-hand side of the equation. This is all we're going to be focusing on today. When we get to Wednesday, I will come back and talk about big F. And we'll talk about, well, what do we do if the right-hand side is not 0? But for today, it's going to be 0. And so that means that we're really just looking for the kernel of L. Oh, we're just looking for the kernel of L. Well, the kernel is a vector space. So enter linear algebra, right? It's a vector space. It means it has a basis. It has a dimension. And it turns out that the dimension is exactly n. It's even better, right? The n is just the n that comes from the order of this differential equation. So that is a beautiful thing. And right on Wednesday last week, we did an example, right? This was the example. I just wanted to remind you one more time what it is here. Suppose we have d squared plus 1. Now that's second order, which means that my kernel of L is 2-dimensional, n is 2. So this differential, here I wrote the differential equation in sort of more of a familiar calculus notation. Y double prime plus y equals 0. I know that there's got to be 2 basis vectors for the solutions. And we did this last time. I don't remember who it was, but some people in the room figured out, oh, cosine of x is a solution. And oh, sine of x is a solution. So you have those solutions there, and they form a basis for the kernel of L. They are Li. Why are these Li again?
There are only 2 and they're not linearly scalars of each other.
Okay, there's only 2 vectors and they're not scalar multiples of each other. That's exactly right. So these are a basis. If they're a basis, then they span all of the general solutions to the whole differential equation. So powerful stuff up here, guys. It may look pretty simple. It may look like, oh yeah, I knew how to solve that differential equation. Back in Math 150A, I could have done that. But I want us to appreciate the nuances of this a little bit more carefully now. The fact that the linear algebra is actually playing an important role behind the scenes here. It's a big deal. Any questions on this? This is just, all of this was from last time. I just want to, especially on Mondays, I like to come in and kind of get our heads back at the game again. It's been a few days since we thought about these ideas. I get my own head back in the game after a 40-mile hike. Get myself thinking clearly about this. Well, there is an issue that I could see right away that we really should talk about. Is what if there was more than just 2 solutions? This linear independence that we're trying to argue here about saying, well, it's 2 vectors that are not scalar multiples, that goes out the window the minute you have 3 or more solutions. So let's get that addressed first. In fact, I'll phrase it here as a question, and then we'll answer the question in just a second. So the question is, given n solutions, so not just 2 solutions, what if we have n solutions? Let's say y1, comma, y2, comma, dot, 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 comma, yn. We have n solutions to our associated homogeneous differential equation, L of y equals 0. If we have that, the question we might ask is, how can we test? How can we test them for linear independence? If I have a lot of functions, we can't just talk about scalar multiples. Now, when we were doing linear independence back in chapter 4, you probably remember that, well, oftentimes what we would do, right, is we would put the vectors, we line them down in the columns of a matrix, and we would like do EROs or something and like figure out whether there's any free variables. That sound familiar? That's what we did in chapter 4 when we actually had vectors with numbers that we could lay out into the columns of the matrix. The problem here, though, in chapter 8, guys, is that my vectors are things like sine and cosine. They're going to be like calculus functions. And it's like, well, how am I supposed to lay those into the columns of a matrix? That doesn't really make any sense, right? I don't really know what that would look like. So it turns out we're not going to do that at all. Okay, we're going to have a different, we're going to have a different answer to this question. We're not going to do anything that's like what we have talked about before. We're going to find a new tool here, a new technique. Let me come over here. And the answer to this question, how do we test for linear independence? We are going to use something, it's got a fancy name. It's called the Wronskian. Okay. Now, I could have talked about this back in chapter 4. And in fact, if you look at our book, it is mentioned even in chapter 4. But I didn't really want to use it until we really need to have this tool. And now is when we need it. Okay. So let me write down what this Wronskian is and how we can use it to test for linear independence. Okay, so this is just a quick definition, right? So I usually will, of course, just use W for the Wronskian. And we're talking about the Wronskian of y1, y2, and dot, 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 up to yn. And this is simply going to be the, okay, so I kind of lied to you guys. I think on Wednesday last week, I said there would be no matrices in chapter 8, no vectors, no matrices. I have one little exception, which is right here. We're actually going to take the determinant of a matrix. Okay, so it won't be bad though. Trust me, it's not going to be that bad. What we do is we put our functions right on the first row of the matrix. So going across the first row, y1, y2, dot, 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 up to yn. That's the first row of the matrix. And what we're going to do to fill out this matrix, guys, is we're just going to take derivatives down the matrix. So on the second row, I'm just going to take the derivative of everything that's on the first row. Okay, so we just take the derivative of those functions. This is all happening inside of this matrix. The next row, I just take another derivative. So y1 double prime, y2 double prime, and dot, 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 yn double prime. The question you might ask is, well, how long do I keep doing that? It's actually very easy to figure it out because you just do it until you have a square size matrix. You're taking the determinant after all. It's got to be a square size matrix. So if you want to know precisely what it would actually be n-1 derivatives of all of these functions. But you won't need to worry about this too much because you're just going to take those derivatives until it's a square size matrix. Then you stop. So this is called the Wronskian. That's what this is. This is the Wronskian right here. And please be aware, keep in mind that the entries in this matrix are not numbers, right? This matrix is filled with functions. So these are like functions of x. There's x's everywhere inside of here, right? And so it becomes a determinant that will have an x in it. In general, it'll have x's in it. And that is then the basis for the theorem. This is the test for linear independence that I said I was going to use this Wronskian for. So let's write it down. Get my notes here so I get it exactly right. So here is the theorem, guys. If there is a value of x, let me give it a name. Let's say that we're going to call it x naught, such that the Wronskian, which is W of y1, comma, y2, comma, dot, 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 comma, yn of x naught. Remember, the x is just the variable that's going to be appearing in the matrix. If you can plug a number into that Wronskian, and if the determinant of that matrix is not 0, aha, if the Wronskian is not 0, then your functions, which are y1, comma, y2, comma, dot, 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 comma, yn, then that set of functions is Li. So if there is even one value of x that makes this determinant not 0, then your functions are Li. This is the theorem that we're going to be using. Okay. Again, why do we care about this? Let's just zoom out again for a moment. I want to know if my functions are Li so that I will know that I have a basis for the solutions to my differential equation. That's the big picture of what we're trying to say here. Yes, Nathan?
That means W of x naught, so you're gonna be plugging in x naught for every one of those y's then, right?
Yes, you're gonna plug in x naught everywhere in this matrix. That's exactly right. Let's just do an example or two of this, just make sure that people understand what's really going on with this. In fact, let's start with the example that's kind of already on the board right over here, sine and cosine. What would happen if we took the Wronskian of the cosine of x and the sine of x? Let's just try it out. So we take, this is like y1 and y2, okay? So I'm just gonna take a determinant and I'm gonna make a matrix here. The functions that we are starting with go on the first row. So cosine of x and sine of x. We just lay those into the first row of this determinant. And then for the second row, I just take the derivatives of those. Right, so the derivative of cosine is negative sine of x. And then the derivative of sine is cosine of x. It looks just like that. Okay. And I can stop because it's a square matrix. It's just 2 by 2. I don't take more derivatives because it's already a square size. And now I've got my 2 by 2 determinant formula, right? AD minus BC. That's just going to give me cosine squared of x. And then it actually turns into plus sine squared of x. Has anybody ever seen that expression before?
One.
This is just 1, right? Actually, these two functions are super Li because we don't even have to pick an x. The Wronskian is always equal to 1. It will never be equal to 0. So, you know, we don't have to worry about the x naught business here. We can just pick any x. It makes no difference. The Wronskian will be equal to 1. And so this implies that my two functions, cosine of x and sine of x, that set of functions is therefore Li. Absolutely. It is Li. Okay, great. Let's try a slightly bigger example than that. Again, for these two functions, we could have just said they're not multiples of each other. But what if I had something like this? Let's try to show that e to the x, e to the 2x, and e to the 3x, that those are still Li. E to the x, e to the 2x, e to the 3x. Can I use the scalar multiples reasoning now on this? Can I just say, oh, these aren't scalar multiples of each other, and these aren't scalar multiples of each other, and neither is the first one and the last one. There's no scalar multiples, therefore they are Li. Can we just say that? It's not legitimate, is it? Unless the matrix is, unless there's only two functions, right? Because here we have three, right, guys? I can give you tons of examples, right? Here are three vectors, none of which are scalar multiples of each other. But they are LD. The third vector is just the sum of the first two. So you gotta be a little careful with that, right? So just because there's no scalar multiples up here, that does not mean that they are Li. We need to argue it a little bit better than that. So let's use the Wronskian. That's what we were bringing it in for, right? So let's try the Wronskian. I'm gonna do a solution here. So I'm gonna do W of e to the x, e to the 2x, and e to the 3x. This will be a determinant. This one's a little bit bigger, isn't it? This time I have 3 functions. So I'm just gonna lay my functions into the first row. E to the x, e to the 2x, and e to the 3x. Just lay those out on the first row of the matrix. And I just start taking derivatives down the matrix, right? So the derivatives, just gonna go like this. Okay, so I'm pulling down the coefficients. And then when I take another derivative, I'm gonna pull down even more coefficients, and I'll get a 4 e to the 2x and a 9 e to the 3x in the bottom right corner. Does that look okay to everybody? So this is the determinant. This is what I meant. This thing is filled with x's everywhere, right? Same thing happened here. It's just got x's all over the inside of that matrix. Well, to do this 3 by 3 determinant, what would be the method that you probably would be considering using? The arrow method? Yeah, let's use the arrow method here. So I'm gonna remind you how that works. We just recopy the first 2 columns here. I'll just recopy the first 2 columns, and then I just draw my arrows. Now, one thing I want to point out, guys, when you do your arrows, let's just look at the first arrow real fast. You see this? E to the x, 2e to the 2x, and 9e to the 3x. Do you guys agree that every one of my arrows will have an e to the x somewhere, an e to the 2x somewhere, and an e to the 3x somewhere? Yeah, and I can actually just kind of factor that out of all 6 terms of my arrow method, right? And it actually would be e to the 6x if you do that. E to the x, e to the 2x, and e to the 3x is the same thing as, when I multiply those, is the same thing as e to the 6x. And now I'm just going to look at the numbers, right? 1 times 2 times 9, that's 18. And then the next arrow, 1 times 3 times 1, that's 3. The next arrow is 1 times 4, which is 4. And now I go the opposite way, right? So my arrow method this way, minus 1 times 2 times 1, so subtract 2. 4 times 3 times 1 is 12. And 9 times 1 times 1 is 9. And I just simply factored the exponential parts completely out of it. Okay? And if you look at this, if you add all of this up, 18 plus 3 plus 4, minus 2 minus 12 minus 9, it actually comes out to 2. So just to simplify that really quickly, it's just 2e to the 6x. Yes?
Like, Rick, if your x naught was like infinity or negative infinity to make it 0.
Cannot choose infinity
So this
or
is
minus
Li.
infinity for x naught. Pardon?
So this would just be Li then.
Right, right. We cannot use an infinity or a minus infinity in this. So the question is there a value of x that you can plug in such that this will not be 0? Sebastian?
Any value?
Any value. Exactly. The exponential function is never 0, and I'm multiplying it by 2, so it's still not 0. This is not 0. So this is an easy win, guys. Easy win. Doesn't matter what x naught you pick, you're always going to win for this particular function. This is the non-zero Wronskian. Okay, great. So e to the x, e to the 2x, and e to the 3x is Li. It turns out, we're going to do some group work in just a minute. By the way, I passed out a group work already. Does everybody have the group work that I passed out?
Yeah.
Anybody not have it? Gus and Nick. pull that out, if you would, for a second. Take a look at problem number 1. Look at the very first problem. The first problem actually, the first problem actually says that as long as you have 3 different values, so you see there the y1 is e to the ax, y2 is e to the bx, and y3 is e to the cx. As long as the a, b, and c are all distinct, as long as they're all distinct, the functions will be Li. So this same Wronskian thing that we just did with specific numbers right here actually works for A, B, and C. So in a couple minutes, we're going to break up into some groups and I'll let you guys see if you can show that. If you change the 1, 2, and 3 to an A, B, and C, see if you can like do all this math and get that the Wronskian is always non-zero. Okay. By the way, when you get to that problem on your group work, I'm going to write a little expression over here that's going to help you. It turns out you have to factor something, and it's kind of tricky. I actually struggled with it myself for about 45 minutes. So I'm going to put that on the sideboard. You can refer to that. You'll see where that comes up when you actually start working it out. Before we do this, though, I just wanted to take a minute to do one more example, because by now you're probably thinking, oh, well, aren't we always going to get a non-zero Wronskian? So I thought I should show you an example where that doesn't happen. If we were to consider, let's just say 3 ln of x and 8 ln of x. Just do one example here where it's kind of obvious. And notice that these two functions, right, they are not multiples, or they are multiples of each other. So are you expecting that these are Li, or are you expecting that they would be LD? LD, right? They should be. Let's check the Wronskian. Let's see what the Wronskian tells us. The W thing, right? I'm just going to call it W here because I don't have a lot of room. So I'm just going to do the Wronskian. I'm going to lay out in the first row 3 ln of x and 8 ln of x. And I'm just going to take derivatives down the matrix. So I just take those derivatives right down the matrix. So the derivative of ln of x is 1 over x. So I just get 3 over x and 8 over x. And now let's just do our little 2x2 determinant formula, AD minus BC. It looks like I'm going to get 24 ln of x over x minus 24 ln of x over x. Is it possible to find a value of x, say x naught, where the Wronskian is not going to be 0? Can you plug a number in for x here and get it to be not 0? Go ahead, buddy.
X is greater than 0. Anything x greater than 0.
If x is greater than 0, what am I going to get?
0.
That's the point, is that I always get 0. Exactly. So this is actually always 0. There is no x naught. We cannot plug in a number here and get a non-zero number, and get a non-zero Wronskian, right? So the vectors, or I'll say the functions, are LD. In this example, they are definitely LD. Okay, so far so good. Go ahead, Nathan.
Do you have when you're getting these functions, are we still having to guess for them?
Are we having to guess for them? What do you mean?
So like say we solved we're doing a linear differential equation and we got e to the x, e to 2x, and e to 3x. Did we have to guess for those?
Yeah, for right now, I'm just giving you these functions. In a little while, we'll learn how to come up with those for ourselves. That's the second part of the class today. Okay, here's what I'd like you guys to do. I can see people are a little tired. I think a good remedy for that is to get you up and out of your chairs for a little bit. Try these two problems. By the way, the second group work problem, the second one is actually, I want you to prove this theorem. It's kind of intimidating when you first look at it, because it's like half of a page. But actually what I did there is I laid out step by step by step the reasoning you need to go through. My first class handled it relatively okay by just following the steps there. So let's try 10, 15 minutes on this. You guys can come on up, grab some partners and see what you can do. I will be around to erase and also to help if people need it. Get rid of all that.
We have a lot of data.
Grab 2 or 3 people and there's markers up here.
I have a question. That was loud.
Thanks, guys. There you go. You bet. I'll try to help out. You might take that example, more or less off of that. And when you get stuck, that hint in the top right corner of my board might actually be helpful. Or if you get stuck. And I'll be around.
Well, yeah, but you have to multiply. If I remember, yes, easy AX. Zero, right? Down to e to the AX. Times e to the bx.
Oh, yeah.
Times
What
e to
Kang is
the
doing, factoring the exponentials out, that's
Both
what.
exponents, we can add it all
Yeah,
up.
it'll be a little easier, less messy.
AX plus bx plus cx. Dx. Not easy. No. See, right?
Oh, that's actually how it would be. It's not really.
Yeah. So the first one.
Okay, good job, guys. Whoops, these are not quite right. Like the first one is BC squared. Fix that a little bit.
There's no way it's gonna end up being 0.
We want this to be not.
And then we go up.
Of course, this part's not. Then you're looking at the part of parentheses saying, I want that to be. Really try to square B. Why not squared C? I tried factoring. C squared, C squared, backwards. I just literally. felt like, okay, this has got to be high school algebra. It should be. And I finally figured it out. Sure. You guys got it all up there?
Well, this isn't.
Yeah, it would be skip the X, the
I think they're wrong.
Yeah.
This is only.
But if you just want to use this. Make sense? Okay, great.
Oh, wait, no, this is.
Anybody need help?
This must be. Because this is, these don't.
Okay.
None
Yeah, no, I think.
Comes off of this. Can we?
Yeah.
Can we just quickly?
Not even zero. B minus E is zero.
No, just double check.
Oh, math doesn't believe me. I don't believe you? No, you're multiplying it out to check that I did it right. I'm pretty sure, well, you guys will let me know.
Well, sir, would this be correct? Basically, no value, it's not like zero, but only two fixes.
Yeah, the point is this is not. This is not zero because this one's not zero, this one's not.
Something doesn't work out. Oh, just that. No, there's probably a plus sign in this. Try to get that.
Already assigned and then the exponential is also not. So you have one number.
I mean, I think we pretty much got it. We squared this question.
Yeah, exactly. You got it. You got it.
And not fixed matrix, right? Yeah. I can factor each column.
I think you should just trust me. Yeah, this term can't be right here. B squared, A squared, something. That should just be B, A squared. Anyway, yeah, it's a matter of being just careful and patient with it, but you can just trust me. You can just trust me.
Yeah, pretty much.
You guys trying to factor
Usually I
that?
write it as columns.
I tried for 45 minutes.
As long as this is.
High school algebra, like, surely
That's
after
exactly what
all
you're
my
gonna say.
years of math, I should be able to figure this thing out. And I just was not. Still, let me figure out that what all this thing is right here in red is exactly that when it's fully
So what we're
factored
trying to
out.
make it equal.
So you can just take my word for it. It's really the main point. of the
C1 times
problem.
Y.
Yeah,
One
R is gonna factor.
C and that. And then
Feel free to just
overdoing
steal
it,
that.
adding all these up and finding ways to.
So basically it's the same.
I was supposed to. Yeah, we plug it in.
Anybody need any help?
I just think ABC is not separate. Yeah. We also have an EB.
Are you having some trouble with that?
So basically, yeah. And only we get no free variable, you know what?
This is always.
As long as those don't. As long as these don't. As long as it doesn't equal zero.
Play around with it.
Even this is a zero. So as long as this is zero. So like.
eventually.
I don't like it.
Oh.
This is exactly like that.
1 twice n minus 1 times.
No, this is zero. No, I'm saying. They're all different values.
We'll-
You can figure it out somehow.
No, because we don't know what, we don't know they're exponential. So this would be, you know, x squared times x, they're not even yet. They can be anything.
Wait, so do we just get to do it?
It's working out here, guys?
It's
Not
done.
zero, not zero, not zero, not zero.
As long as this
I love it.
zero.
Great job.
I'm only one.
This is only zero.
Oh, so perfect.
Yeah, okay.
I will let you think on the next steps. Is it working out?
Yeah.
Right, this is not zero, this is not zero, this is not zero, this is not zero. You're multiplying everything that's not zero, so the result is not zero.
If you don't know the function.
Yeah,
it's the old
Yes. That is correct. Good job, good job.
Unless
So
that's
for
something
example,
else.
I'll do the first one, so between y prime 1 and y prime 2, right? Hello, Alfred.
That's good, guys. Good. For part A, what
I can see where that
shows.
So,
Which basically, so what are the variables?
C1 equals C2 equals C.
What will C1
That's
equal
what
C2?
I'll have to use it.
Great, that's the key. So you're trying to show that all the constants are
All of them are.
Good job, good start. That looks good for
What is
part
it?
A.
It's just that thing
Good
that you
start.
put to show that something is.
Yeah. I minus 1 time, right? Like it's minus 4 times, 5 times, and so on.
Like right now, it's
It is repetitive.
differentiate.
So is this one the-
Alright,
oh, this one.
when you start with this,
Is this
then
one
all the
second?
constants
Or is this one?
exactly.
No, no, they're.
Yeah, it's not, this one is going back to chapter 4.
So they all could be different. This could be like.
So that's why one
Oh, yeah.
Alright,
So what you get is you get.
so that's what the rest of the steps are gonna show.
You get
Hopefully, I'm
C1
gonna leave
times.
these already loud. Oh, you know what, guys, I'm sort of trying to do it all in power. I would argue that the derivative of this is literally just, you know. You're not.
So you literally just get
N minus 1 time. Let's call it C. I just want to get C, so that would be like. And then, how many
Same thing.
how many goes more to this? So N minus 3.
It's a.
So what are we trying to show for linear independence? We start with this equation. Just going way back to chapter 4. Have a set of vectors and I want them to be Li. I make a linear combination of those vectors.
And then.
I set it equal to 0.
Oh, so this is basically set us up. The matrices need to be the same, right?
They need to be the same and they need to be 1.
This is literally like.
With zero.
Yes.
So C is actually
You
not a
guys
number.
remember that?
So
The
that-
definition of linear independence.
You just have to have it.
And then I mentioned C is zero.
That the constants are
He has a
all
matrix.
zero.
So what is that?
That's going to be the case.
There was a question like that.
There was what?
There was a question like that in the homework.
Oh, yeah.
Like a theory question.
Oh, yeah, these are always theory questions. The definition of
You
linear
call it this
independence.
basic.
Does anybody need help?
Usually this is A times C.
I forgot how it started.
So.
You guys get the first one wrapped up?
Well, usually A would be the matrix is number, right? C, the vector, C would usually just be something like the
Like
tall
C1,
one, right?
C2.
Good
So I would
guys.
think this would be
And then
I actually think it's
A,
all the variables,
then A would be.
Like this part.
right?
We need to show.
So
Yeah.
You're gonna try to put this in group A.
So this.
That's part
This is like
of C, yeah.
I think
We
that's
need
just.
to make a matrix that shows us.
And then this is gonna.
Yeah.
I think so.
Yeah.
Yeah.
Why don't you try to write it down? Yeah, you can just try to
We
write it
want
down.
our output to be an n by n matrix, right? So,
No. Let's see that. Still, the constants are zero.
That's right.
And the way you do it.
So it'd be Y1 C1. No.
Pretty good so far, guys. Good job.
yeah, that's
You
what-
don't know.
Oh, yeah. Because it's, because what you get is Y1 C1
Yeah,
plus
because
Y2 C2.
this is, I don't really know how to do this.
Yeah, no, this is right. This is right.
Just but then that would be.
How does this relate to what we're doing?
That's my question.
No, no. So we get C1.
Seen that guy with the sleeve.
C2.
Have you seen the guy that can draw like a huge whole arm?
No.
He basically does the exact same thing, but like this one.
So you get four. You get.
Yes, for us, yeah.
Do you remember what that is? Sort of like-
It's just we don't erase the word. You're good, you're good.
How is it related?
That's correct, that's correct.
It's just the matrix we use. It's a matrix that we did determine.
We would do the determinant of A. I think you just ignore C.
Oh, wait, very good.
They were.
Factor.
You can just say like, take it to
The entire row to the entire column.
Is whenever we put them into the
right? So this is basically just all. That's basically the answer.
So there's a hand on
Yeah, no, but I think what it's trying to get at is factor out. Like those constants, like, you can take them out. It's what it's trying to say.
Say again?
And then like this is. equal to
That's
three
right.
or something.
That's right. They all need to be zero, exactly. So that's
Oh, we
actually
can
part of
turn it
it. State what it is.
It's more hard to do this.
C1, Y,
So to include this or that.
It's a multi-factor.
Answer is just not.
C1, they're all different.
Yeah, this would be A.
AX
This would be C.
equals 0,
And
and
that's the
then
first thing, and then the
For
second
Y1,
part, they're gonna ask
zero
for
Y2,
derivatives.
dot, 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 YN, and whatever. And then you could just put
Yeah, how would it
C1,
relate?
C2, dot, 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 CN,
But
and then
this
just
here.
multiply out.
Okay, I love this.
Okay, wait, maybe let's go into what you're talking about. So what happens in factor?
Yeah, also really good.
Do the
No,
wrong
no,
thing.
it's the original function and then. The other side.
What I actually need to do is.
I don't really see why we.
Oh, I see, so this is like our X.
Yeah, that's our X, yeah.
That's basically the X. And this is our
Yeah, A, yeah.
square matrix.
Yeah.
I think. I don't know.
So you're like, what if all of these end up being zero?
Okay, so you know, we have our C1 Y.
Yeah.
That's effectively this, but we have our 1 by whatever, whatever by 1. So this is just imagine like that, equal to 0, and we're turning it into.
Is this equal to zero?
This is literally.
Just try to like imagine, so we got Y1, Y2, and YN. We got this is our A, because remember the AX equals 0? So we got X, Y, Z. I get this equal to 0.
No, no. So this one here, yeah.
So it'd be Y.
Because why you say we haven't done
To make a Wronskian of this,
Yeah.
that's gonna be our A.
No, we have to
This is gonna
prove
be
that
our X.
only if there's.
You get what I'm saying?
So that.
We wouldn't have a list of X's, it would all just be one number that effectively makes it 0, so I guess it's kind of the same. And this is like, probably leads into the second question, like how many derivatives do we need on this side? We need 1, 2, 3, and it's basically.
So the first column is all the y ones, is all
And
the
that's one
derivatives,
column.
second column is all the derivatives. This is
Oh, cool.
the matrix where you have the functions on the first row, and the derivatives.
Oh, yeah, it's
on the
AC
second
equals
row.
zero.
No, because this type is equal to zero.
Yeah, so this is our third.
Yeah.
So this is all zero.
Now, the Wronskian is the.
Yeah, but these are our little XCs. Yeah.
So what column is this one? How did you include it?
Yeah, it's all.
Yeah, because I mean, A can also be equal to that.
Or, I mean, it's like a mesh of everything, but I guess we probably should just for clarity. Just like,
Yeah, we can actually go.
Yeah.
Either A or C.
What do you know about? I don't know.
That's the only.
So this is an invertible matrix. This is A. Times, we're gonna have C.
Zoom. Hey, Zoom.
And now we have this little equation,
I'll be immortalized on top of that.
and we've been told that capital A is invertible. So I guess we can take advantage of it.
Someone like random.
He said he was sure.
What's
This
this?
is me waving at the board.
Yeah, that's the only thing up there.
That's given to the top. Yeah, so guys, the matrix A is actually the one that is related to the Wronskian.
Differential matrix.
Yeah, they told us that it's not real.
Yeah.
So what's that tell you about a matrix? If the determinant of this matrix is not zero.
Oh, hey, what is the third calculus?
Right, because you can basically.
Oh, no, that's what the determinant right? This times this is still equal to 0. I don't know.
Because I wanted to let you know about this cool thing.
Does anybody need a hand?
Where you can, I don't know what the rules are.
Does anybody need a hand? You guys doing okay?
Matrix, so we got.
Yeah.
Y1.
Right. Exactly.
It will be like our X. So we like see
As a column.
Yeah.
Exactly. Beautiful. Beautiful. Right. And then the derivative, so you can just take the derivative, you can take this equation and take the derivative of it if you want. And then that makes another row, right?
Yeah.
Yeah.
No, so these will be always be constant.
Right, they're just gonna be as a column on the side. And what is this matrix I'm making here on the left? The one we did earlier, right? It's the one that's related to the Wronskian. The Wronskian is just the term as a. There's a connection.
Yeah.
Something to do with those.
I think about it for a couple more minutes. You guys feel pretty good about it?
Yeah.
See? I'm not smart about it.
Yeah, you're welcome. You guys doing okay?
I'm gonna guys have this.
Right, because
I think it's
because
something
A,
like
because A, the determinant of A is not zero.
So then C
So
is.
we don't really need to put the C in there, just put just the first one, just this matrix here. It is an invertible matrix by assumption. Right, if they told us the determinant is not zero, so that means the matrix is invertible. And if it's invertible, then we can cancel it. Well, sorry. Yeah, so yeah, you're gonna cancel the A, then you're gonna get the C, the C's are all zero. That's right. Yeah, so, yeah, looks good to me. Looks good to me. Hey, guys, I can see that a lot of folks are done, not everybody's completely done, but let's do this. Let's take a 10-minute break. You wanna go stretch your legs outside, take 10 minutes? During the break, oh guys, real quick, during the break, if you have any questions on the homework that's due tonight, feel free to jot them down here, and then after the break, I'll be happy to try to help you out. I'll see you guys at about 3:05. Let's do 3:05.
Sometimes when it comes to math, it's like getting into an argument, and then like when you get in the shower, like 3 hours later, you know, like your fire comes back. But like you already took it, the test, and you're just like, oh no. Like, I could have done it like this. I could have flamed something like that. I mean, it's kind of like away from linearity, but not away from linearity. Getting more into my strong suit again. Make me feel good about myself. Do you watch Marvel movies or no? No?
I mean, I know.
Oh, well, I went, well, first I went to get a massage. That was my biggest thing. I went to like a Thai masseuse place. Oh my God, the lady was literally walking on me. She had me like laying down flat and she was like just walking on me. And then I got scared. She's like, okay, 1, 2, 3, she jumps on my back. And like, but the whole thing kind of like, it felt so good, but I was so scared. And plus she got me like into this weird positions and then she grabbed my neck. I'm like, okay, I'm done. And she like cracks my neck. I'm like, oh, it felt so good, but I was like, I never been so vulnerable in my life. And then the second day I went to the gun range. That was really fun. The gun range. That was really fun, but it was really expensive though. It was like $1,000 for 2 people. Just me and my girl. And I've been saving up for this trip for like 6 months. So I had it. But still, my bank account just went from like, and I lost like, I want to say like 60 points on my credit score because like I was using on my credit card a lot. And like you're not supposed to do that. I don't even know, because like which is so dumb because I paid it back in full. I didn't do payments and I still lost points. I was like, whatever. No, it's just doing things. So like I went to I don't really gamble. I just gamble. I think I gambled like $150. But like I just spend more on shows, on things, and thankfully I didn't spend it on clubs. Because I had a coworker and she brought her cousins, and so there were like 3 of them, and then no 4 of them, and then me with my girlfriend. So I pimped out all of them. There's like 5-to-1 ratio, so we got it to free. I was like, because he was like, how many girls you got? I'm like, I got 5 girls. I was like, okay, cool, 5-to-1 ratio. Come on in. I was like, let's.
They do that?
Yeah, they do. They usually ask for ratio. They usually pay. Yeah, because they want to like promote more. Because there's more girls in the club. Obviously, there's more guys in the club too.
I see.
Yeah, so if you're gonna if you go to Vegas, just try to get like a bunch of like all your lady friends together, and then you believe me, just I'll be like 1 to X ratio. Like if it's more than 3, you're like, oh yeah, 1 to X ratio. I'm like, get it for free, easy money. And they're usually promoters too. If you walk around Las Vegas Boulevard, the strip, they're usually guys in suits like just promoting. You can get them for free. Usually, they just like give out like it's like, oh yeah, like if you want to come to you, like just give me your number and they text you a number and like you're like, oh yeah, you're on the list. And you do that. And you go to the club, you're like, oh, you're on the list. You get it for free. Either or. It is kind of, yeah, it was fun. It's been a lot. Oh my god. When dinner was like $400. I went to Gordon Ramsay place because I'm such a Gordon Ramsay stand. It was pretty good. Gordon Ramsay has really good food, especially the burgers. That was fire. I recommend burgers rather than his actual restaurant. We didn't get a reservation for Hell's Kitchen though. The next reservation at the time was like a month after. Like so we went in March And the next reservation available is like in April 18th, which is like, oh, which is today. Yeah, no, they're like booked like a month ahead. So you have to take, you have to like really schedule your reservation in advance. Yeah, so we only got to the pub and grill and the burger place, which was really good. Rather expensive though, but still. It was good. I mean, you don't have to spend a lot. I just wanted to go all out. Yeah, then I drove a Lambo, which is like $300. And you can like go as far as the instructor that was like with me. Like he told me to go fast because I'm so used to driving like a normal person. Yeah, so he's like, oh no, you can go 150 if you want. I was like, he's like, I'd rather not. Because like if you crash, he's like, make you go through like a whole like tutorial, like not like just for like a whole seminar before you drive. He's like, oh yeah, just please don't crash the cars or you can have to pay for this. I'm not paying for a Lambo. I'm just a poor college student. So I just went from like 70 to 80, like half of it. Yeah, they kind of scare you a bit. I mean, they don't scare you, it's just like you can go as fast as you want. Don't crash. This is like how the track goes. It's like a little. It's like there's a straight line, and then there's like a hard right, and then you can then a hard like a little roundabout to go in a lap. Yeah. So the thing is, like you're supposed to like gun it, and then brake as hard as you can, and then turn right, and then like kind of like drift around. It's like I was like he's like do it. He's like no, I don't want to do it, and he grabs it because like they kind of hold the wheel for you. And like he tries to, I'm literally fighting this dude. And it's funny because like they record you, so you can like share it with your friends and family. You can just see me fighting with the guys. Like pivot. They're like, no, I don't want it. I'm scared. Oh, so basically answer the whole question. C will be A, so A was C. Dr. Anna, have you ever hiked up on mountains in Altadena?
And where?
Altadena, like around like north or like Pasadena?
Well, I've done Mount Baldy, Cucamonga Peak, Ontario Peak. And Mount Baldy is the tallest one over there.
Okay, I only done like.
Yeah.
Like it's a.
Yeah, Baldy is an ultra prominent mountain. There's only 57 of those in the lower 48 states.
Ultra prominent.
Yeah, it means it has more than 5,000 feet of prominence. And there's, huh?
I never heard of that.
Yeah, so the prominence is if I'm standing on top of Mount Baldy and I want to walk to another mountain that's taller than it, I would have to go downstairs. I would have to go down at least 5,000 feet before I could climb back up again. So yeah, Baldy is there's 9 ultra prominents in California. Yeah, I've done about 22 of the 57 in the lower 48, and then there's a bunch in Alaska, which I'm not gonna do, but no, probably not. But I am hoping to do a few more. There's actually several in Nevada. Should probably go over there and do those at some point.
San Jacinto one.
San Jacinto is another one. Baldy, San Jacinto, and San Gorgonio. All three of them.
As well.
Yeah, all three of those are ultra prominent. Yeah, that's absolutely right.
Yeah, I actually want to show you this. They got this beautiful view.
Oh, wow. Yeah, that is really stunning.
Yeah, especially in person, like I
Yeah.
was so taken aback.
Yeah, that is the stuff I live for. I love,
Amazing.
that's right. I love that stuff. Okay. All right, guys, I think we'll go ahead and get started again. Thank you very much for your hard work on the group work. As always, the solutions to the group work are available in Canvas, so you can go back and review those at your leisure. We got a couple of questions on the homework over here. I will try to save a few minutes to look at those in a bit, but I want to make sure that I get through this next little section, if you don't mind. This is section 8.2. This is one of the friendliest sections of the entire semester. The homework on this section, which is the one that will be due next Monday, is hopefully going to be like a 30-minute crank it out kind of job. It shouldn't take long. It's very, very computational. So what are we doing in this section, 8.2? We are finally, at long last, going to learn how to solve these differential equations. This is an entire family of differential equations, and we're going to learn how to solve them. What do we have here? We have nth order, we have linear, we have constant coefficient, and the equals 0 is why it's homogeneous, right? Homogeneous means it equals 0. What am I talking about with the constant coefficient stuff? I just mean that the A0, you might remember when we first wrote it down, A0, A1, and so on, those could have been functions of X. They could have had X's in them. For this section, we're going to assume that they are not functions of X, but they are just numbers. They are constant numbers, okay? If we have a differential equation like this, then in the next half hour or so, we're going to learn how to solve it. In other words, how to find the general solution. And again, for most engineering applications, do a mass spring system or you set up an RLC circuit, you are going to be looking at these types of differential equations: constant coefficient, linear, homogeneous, nth order. Okay. So it's a good family for us to learn how to solve. So of course, this is right here. This is just my big L that we've been referring to in the notation throughout this whole thing. And let me just give you the method right now for how to solve this. The method to solve this. Okay, you ready for this? The method, how do we solve these types of differential equations? Drum roll, drum roll. We guess the solution.
Is that the only?
We guess the solution. This sounds like the way I took my SAT exam. Basically, just going to guess the answer and hope for the best, right? I mean, this is actually one of the things that I found very occasionally, I will say, I find this unsatisfying about differential equations, is that people just guess the answer. Well, let me elaborate a little bit about what I mean here. What I really mean is that there is a trial solution that is sort of standard that we can try to plug into our differential equation and see if we can make it work. Okay, that's actually what I mean. So let me just clarify that a little bit. When I say guess the solution, what I mean is we plug in something that is called a trial solution. It's a solution that isn't totally fleshed out yet, but we plug it into the differential equation and see if we can make it work. And there is a specific trial solution that goes with this type of differential equation. Everybody's going to want to know this. It is simply y of x equals e to the rx, and this will be where r is to be determined. And in a moment, we're gonna determine it. I'm gonna show you how we can figure this out. Now, this does not mean that every differential equation under the sun is solved by trying this guess. This guess works for this type of differential equation. If I come along later with an equation that does not have constant coefficients, then this guess will not necessarily be a particularly good one. So the choice of the guess has to match with what type of differential equation you're looking at. And obviously, if I give you I'm only going to hold you responsible for those differential equations that we specifically look at, such as these that we're talking about in this section. So if you see a linear, nth order, constant coefficient, homogeneous differential equation, bingo, this is your go-to guess. Now, I say here, I'm going to plug it in. Let's do that. Let's plug this guess into my differential equation up here. So what I'll have is a naught d to the n plus a1 d to the n minus 1 and dot, dot, dot. The last term is an, and I'm going to plug in e to the rx, and I'm going to see if I can make this equal to 0. I'm going to try to plug that in, and I'm going to see if I can make it equal to 0. Well, the nice thing about this particular guess, e to the rx, is that it is easy to take derivatives of it. Right? The derivative of e to the rx, I hope everybody remembers, is just simply r e to the rx. And if we take higher derivatives, we just pull down more factors of r, right? So what is this going to be? I'm going to have a0 and then n derivatives of e to the rx. Isn't that just going to pull down r to the n in front of e to the rx? I'm not done yet. That's just the first term. The second term has an a1 on it, and then I have n minus 1 derivatives of r e to the rx, as e to the rx, I'm sorry, which is r to the n minus 1 e to the rx. And I'm just going to go dot, dot, dot. The last term is simply an e to the rx, and we still have equals 0 on the right-hand side. So far, so good. Now, if you look at what's on the bottom of the board here, what sort of jumps out at you that would be a natural step to take next? Right, we can factor the e to the rx out of that. So let's just do that. That's just algebra, right? So I factor that out, I get a to the r to the n plus a1 r to the n minus 1 plus dot, dot, dot plus a n, and then all of that is still equal to 0. Careful not to bump this desk here, Nathan. Okay, so is this exponential ever going to be 0? That's never 0, right? E to the rx is not 0 for sure. And so actually, what do we have left? We just have what would be considered a polynomial that I would like to solve for r, right? If anybody's lost on what am I trying to do right now, I will tell you, I am trying to solve for r. It says r is to be determined, and I'm currently trying to do that. Well, I have an equation sitting in front of me here that I can try to use to do that. This is actually, it has a name, it's called the auxiliary equation for the differential equation. That is called an auxiliary equation. And so it's actually kind of like the characteristic equation. Do you remember in chapter 7 with the lambdas, we would have to try to like factor it out and find the roots of the characteristic equation. So it's basically the same thing here, right? So if I can solve this, right? So we solve this auxiliary equation. Just write this down, right? For r. We just have to solve that equation for r. By factoring and getting all the roots written down, that's going to be the trick. Okay, so that is the name of the game. And guys, I don't know if you've noticed this yet, but this auxiliary equation, how do you get it from the original differential equation? What is the difference between this and this? Everywhere you see a D, it becomes an R, and my friends, that is just how simple this is. This is in the running for one of the easiest sections in the whole book. All you have to do is change every D to an R and then factor it out. Now, of course, it could be some horrendous thing to factor, but you have to trust me. That'll give you something to factor that's reasonable, right? You factor it out, you find the values of R. What are you gonna do with those values of R once you find them? You're gonna write down your solutions that go with those values of R. So let's do an example. All right, let's do an example here. Let's find the general solution. So I'm going to give it to you this way: D minus 2 times the quantity D squared minus 16 of Y equals 0. This is a differential equation. By the way, so the L here, the L is just right here, right? If anybody, if the D notation ever kind of gets you a little bit more abstract than you would like, keep in mind that there is, of course, another way to represent this. We don't need to do this right now, but I just want to show this to you. Right? You'll notice that if I multiply this out, I have a D cubed, right? D cubed means 3 derivatives. So there would be like a Y triple prime there. And then there's if I sort of FOIL out all the terms, I also have a 2D squared with a minus. So that would be minus 2 Y double prime. And then there's a 16D, also has a minus. That's going to be minus 16 times 1 derivative of Y. And finally, 2 times 16 is 32. And then 32 is just multiplied by Y. So, just so you're aware, right, if you don't like the D notation, there, of course, is always the fallback to the prime notation that you'd be very familiar with from calculus. Okay, but in terms of solving this problem, let me just show you. Let's keep track of how much blue I have to write down to solve this problem, because it is not a lot. First thing I'm going to do is write down my auxiliary equation. I'll do that right here, the auxiliary equation. Remember what that means? That just means I change all of the D's to R's. So I'm looking right here. All of the D's get turned into R's. So it's R minus 2 times R squared minus 16 equals 0. Can we find the values of R here? 2, right? Or plus or minus 4. I have 2, 4, and minus 4. For each of those values of R, I can now plug into, this is the important box right here. I can plug those in and write down my solution. So I have y1 of x, that's the first solution, is e to the 2x. And then y2 of x is going to be e to the 4x. And then y3 of x is going to be e to the negative 4x. Those are my 3 solutions. Now, whenever we're trying to write down the general solution, right, we always have to have a basis, a spanning set, to write the solution. For these to be a basis, they have to be Li. Are those going to be Li? Did we all just do the first group work problem? If I have e to the ax, e to the bx, and e to the cx, right? That's the first problem on the sheet, right? 3 distinct values of R. then these are already Li. I'm just gonna say Li by group work number 12. And this was problem 1. So we can just refer to that if we want. That we have those functions being Li by the group work that we did earlier today. And so therefore, we can now write them down as a basis, and so that means I can express the general solution. This is a very quick way to get to the answer, right? The general solution is y of x equals c1 times e to the 2x plus c2 e to the 4x plus c3 e to the negative 4x. Yeah, go ahead, Josh.
What if it's like C2 e to the negative 4x plus C3 e to the 4x? Doesn't matter.
Oh, if you put these in different terms in a different order, it makes no difference. Yeah, it makes no difference. You can list those out however you like. So look at what's in blue there, guys. On that solution, that's what you have to be able to do. So we take our differential equation, we immediately turn the B's into R's, we factor it out, then we write down our form of our solutions, and we go to our general solution here. This is why I said the assignment will take you about 30 minutes to do, because it's just, that's it. There's not a lot else to think about here. But are there any pitfalls that anybody could think about for right now? So I realize that this is all that we needed to do here, but do you see where maybe something could go wrong, Sebastian?
If any of the R's are the same.
Oh, what if the roots are the same? Oh, so don't write anything down on this yet, guys, but what if these roots were all 2's? Then I would be coming in here and I'd be writing, I would be writing the same thing 3 times, and that's not going to be Li anymore. So one of the issues that we can run into, we're going to address the issues here, is repeated roots. Sebastian hit the nail on the head with that, right? Repeated roots of the auxiliary equation. That is something we have to be careful about. So that's one issue. I'm wondering if anybody can see another issue that could come up, also having to do with the roots of the auxiliary equation. Anything else that might bother us? Yes, Nathan.
Would it be okay if R was equal to 0?
If R being 0 is no problem.
So
It would just be,
imaginary
if
R.
R was 0, then you would just have e to the 0, which would just be 1. And
Imaginary roots?
that's it. Imaginary number. When you factor your auxiliary equation, you could get imaginary numbers. Now you might think, well, what's wrong with that? Well, I'll tell you what's wrong with that. Let's say you have an imaginary number, let's say 5 plus 3i, and you try to do this. Good luck graphing that. Good luck even plugging a number into that in your calculator, right? I mean, I don't even know what that means. E to the some imaginary thing times x. Like I would not know how to get a value for that. So this becomes like almost like meaningless. It turns out that mathematicians have, of course, worked very hard to find a way to make sense out of something like that. And it's called Math 412. It's the course that we talk about complex analysis with. But to be honest, if you're working for an engineering firm and you tell them that here's the solution to your problem or whatever, they're not going to be very happy with you, because this is not actually a solution that you can draw a picture of. You can't plug numbers into it. You can't really compare it to other functions of the same nature. It's basically not a good thing to write down. So when R is imaginary, this is not a great outcome. Okay, so let me put that as a second issue. Imaginary, well, let's call them complex. I like to refer to them as complex numbers. So we'll say complex roots of the auxiliary equation. So that's another issue that we have to deal with. So I'm going to take a couple minutes right now and tell you how we deal with those two issues, and then we'll probably be about out of time. We'll spend the rest of the time talking about the homework after that. Okay, so these are two issues that we have to address, and I will tell you a little bit about how we address both of them. Any questions so far? Everybody good? Okay, what happens when we get repeated roots? Alright, so the first issue, I now want to go back. The first issue that's listed here is repeated roots. So if a root R is repeated, now we actually want to keep track of how many times it repeats. It's just like when we were doing the lambdas and I asked you to keep writing down the repeats, the multiplicities. We want to do that here too. Let's say it's repeated k times. Well, let's just say that, repeated k times. Then, if you have a root that repeats, then what we need to do is we get k linearly independent solutions as follows. How do we get our solutions when we have these repeat roots? So I'm going to write them down. First of all, we get y1 of x, which is of course just e to the rx. That's the first solution. But then we need more solutions, right, that are associated with this repeated root. So instead of just writing down e to the 2x over and over again, the same thing again and again, which won't be Li, what we need to do here, guys, is something I call stacking x's. We're going to put an x in front of the e to the rx. Just to be clear, this is not a scalar multiple of the first solution. X is not a scalar, it's not a number, it is a variable here, right? So these two solutions are not scalar multiples of each other. And let's say we have a third solution now, y3. We're going to stack an additional x, and now it becomes x squared, e to the rx. And we just keep stacking like that as many times as we need to. By the time we get down here to the kth term, we're going to get x to the, it'll be k minus 1 e to the rx. So there you go. And it turns out that these will be Li. If you don't believe me that these are Li, how are you going to check it? Say it again? With the Wronskian. Does that look like fun? Not particularly, because of the product rules that are going to come into this. It's going to be really, really messy. So we're going to trust that it's correct. Okay, somebody way smarter than me, way before I was ever around, figured out that this works. These are Li. We don't need to, we're going to try to get away from just always just leaping to the Wronskian every time, right? We're going to take it on faith that these will be Li. So this is what I like to call the X stacking process. When you have a repeated root, and you know how many times it repeats, you're going to create this list of solutions by stacking those X's up there. Okay, so that's pretty easy. I'm not going to do an example of that right now, but we will certainly see some examples of that on Wednesday. Of course, I'll get to quite a few examples of that. Okay, that's the first issue. Very simple. Repeated roots. Any questions on that?
Really
Yes.
quick. Remember when you had 2, 4, -4?
Yes.
What prevented you from making x times each the -4x a solution?
Because, so it's not, so it may work, it may actually work, but it's not as simple as just e to the rx. I would never choose to stack x's unless I have to. Yeah, that's a good point. Okay, let's talk about the complex case. This is meaningless, guys. I can't do this. you don't want to see this anywhere. Like anytime I have to get out my red pen, anytime I see something like that, right? We don't want to have imaginary numbers in the exponents. So how are we going to address this one? If my roots are of the form a plus or minus bi, where b is not equal to 0, then we get solutions. Well, I should emphasize again, these are going to be Li solutions, but I'm not going to do the Wronskian on these. I'm just going to write this down again. So we're going to get two solutions here. And I'm going to write them down here in a moment. I'm wondering if anybody has a thought as to what we're going to do there.
Either the AX, either the BX.
That's a thought. That might be an idea. Do you guys remember the very, very first example we did in chapter 8? It was this one. You remember this one? If you actually look at that, the auxiliary equation, take r squared plus 1 equal to 0, the roots are actually plus or minus I. It's actually a very good example of where you do get, in fact, complex roots. And do you remember what the solutions were?
Sine and cosine.
Aha. They were sine and cosine. So something tells me, isn't that interesting? Something tells me that over here, we're going to use sines and cosines to unwrap the solution. So let me write it down. What it turns out you need to do, guys, is e to the ax cosine of bx. Now, just to be fair over here, guys, on this one, on plus and minus I, just so you can understand that, there's no real part at all, right? A is actually 0 there, and the b, which is the part that's in front of the I, is just a 1. So if A was 0 and B was 1, in the formula that's over there, you would get exactly cosine. And of course, the second solution is going to be e to the ax times sine of bx. Okay, again, checking this with the Wronskian that they are Li is something we are going to bypass. It's a tedious calculation because of the product rule that you would have to have. But it works. It works. It's something that we definitely could do if we needed to. Okay, is this making sense? Now, somebody in my first class asked me earlier, well, what happens if we have complex numbers that happen to also repeat? Right? So now you're dealing with these kind of solutions with the sines and cosines, but then they are repeating. So again, for repeats in this case, so just continuing up to here, for repeats, we stack x's again. So we go back to stacking x's in front of things that look like this. So you could have a y3 and a y, now they come as pairs. Guys, when you have complex roots, they always come as sort of 2 at a time. And so for the first repeat, you would just stack an x here, x e to the ax cosine of bx. And for y4, it would be x e to the ax sine of bx. That would be the third and fourth solutions. Okay, and then if there was more repeats, right, if we had even another round of repeats, third time through, then we do y5 and y6 by using x squared to do it. Okay, so this is for additional repeats of imaginary numbers. Oh man, I would not want to do the Wronskian on this. My goodness, I'd probably stay up all night and I'd get it wrong anyway. Okay, so we're gonna take it on faith that everything we're writing down is gonna be Li. So we're not gonna stop and do the Wronskian. Okay, does that make sense? So like if my differential equation, so just as a quick example, if my differential equation had been b squared plus 1 squared of y equals 0. then what are my roots here? Well, so for the solution, I'm just gonna change all the D's to R's. And when I write down my roots, I have plus or minus I, but they are repeating twice. And remember, I do want you to write down the repeats. When they repeat, we should write them down as repeats. And so now, right, you have y1 of x and y2 of x. They would be just, you know, cosine of x and sine of x, just like in that earlier example. So cosines are just the same thing as what we had before, but the difference here is now I've got to actually have two more terms. Why do I need two more terms? Why can't I just stop with the first two? Just say that's good enough.
Because it would span the entire thing.
It doesn't span the entire thing. What's the order of this differential equation? Fourth order. So the kernel of L is what dimension? Four dimensional, right? So my basis had better have four functions in it. So far, I've only written down two. So that's why we have to go on. And what we're gonna do is just stack x's. X cosine x and x sine x. There you go. This is now going to be your basis, assuming that we trust that they are Li. We're not gonna do a 4x4 Wronskian and try and take derivatives of this 4 times. It's gonna be a disaster, right? Okay, so we'll take this on faith that that is actually the case. Okay, on Wednesday, we will do more practice on this stuff. I'm going to call this pretty good for now so that I can talk about some of the homework problems. But are there any questions here on how to handle these two issues? Everybody okay with the X stacking as well as the sines and cosines stuff? Some of you might wonder, well, how in the world do you get the sines and cosines out of the imaginary numbers? Have you guys seen this formula before? I'm just kind of curious because I haven't taught this class in a long time. If you have an imaginary number and an exponent, have you seen this? This would have been in a calculus class. I don't know if anybody's seen this formula. Is that familiar to anybody at all?
In pre-calc, in trig.
So you saw it somewhere, but just, did anybody else ever see this? Have you guys seen the t-shirt, the t-shirt that's this one has this on it? I'm so old school, I guess. Yeah, this is actually like one of the most famous formulas because it has 3 extremely impressive math numbers that are all related to each other in an equation. If you plug in pi for theta over there, if you plug in pi for theta and you use the fact that cosine of pi is -1 and sine of pi is 0, you actually get this expression, which I have actually seen on a t-shirt before. Not my own shirt, but I've seen people with that on that they've worn. Well, anyway, it's through the use of this. This is actually called Euler's formula. It's through the use of that formula that you can extract these two real solutions from what looks like a meaningless exponential with an I upstairs. You guys look super excited about this. I was going to say, oh, I can derive it for you, but I'm not sure anybody wants to see it right now. We're not going to do it. But anyway, that is actually a very cool relationship between, actually the way this is proved, believe it or not, you use power series. Remember the Taylor series representation of a function? Am I bringing back nightmares? Nobody wants to think about this now at all. Good news is I'm not going to ask you anything about that or Taylor's theorem or anything like that. We're going to stick to the guts of what we're doing here. But anyway, yeah, so I just thought I would mention that that's where these things come from. But if you've understood everything we've done in the last 20 minutes, you can do 8.2 completely. This is the whole section. All right, so what I'd like to do for the 10 minutes that I have left is tackle a little bit of the homework. There are some people who have put some problems up over here for me. I'm going to do them out of order, kind of by choice, and I may not get to all of them. What are you gonna do if I don't get to all of them and you still have a question?
Right.
No, you're not gonna cry, you're going to, huh? Yay, come to office hours, exactly, either in Zoom or in person, exactly, so, but let's see how much we can do. In section 7.2, let me start with number 20. Okay, that's the first one that's down here. 7.2, I'm gonna start with number 20. This is a 3x3 matrix that they give us, so we're totally changing topics now. 1, -3, 1, -1, -1, 1, -1, -3, 3. Now, that is a matrix that has no zeros in it. So finding the lambdas just from what's there would be very, very challenging. Like the algebra of the factoring the characteristic equation would be a mess. Fortunately, they gave us the characteristic equation, and in the problem, it's kind of listed there as like a hint or whatever. And here's what it is. There's what it is. So they gave it to us. This is one way around the problem. If it's too hard to figure it out from the determinant, maybe somebody will just give it to us. So what are the lambda values? If this is the correct characteristic equation, what are my lambdas? Sebastian?
2, 2, -1.
2, 2, and -1, and I appreciate the repeated root. I should probably tell you guys what the question is asking. The question is asking whether this is defective or not defective. Remember, non-defective means every eigenvalue holds its weight. So which of these two eigenvalues would you recommend that I work on first? The one that repeats, right? So that would be lambda equals 2 in this case. So let's do that. We're going to take a null space here. And I have to subtract 2 from the main diagonal. If I subtract 2 from the main diagonal of the matrix, this is what I'm getting. If I subtract 2 from the main diagonal of the matrix, that's what I have. What do you notice that I can do here?
Delete 2 rows.
Actually, all 3 rows are the same, so you can cross 2 of them off and just keep 1. And does that look okay? You get a pivot right there. How many free variables do you have? 2. 2 free variables. How many basis vectors are you therefore going to come up with? 2, right? You're going to get 2 free variables that you can bust out and make a basis from. So is this eigenvalue going to pull its weight?
Yes.
Yes, it will. Therefore, and do we need to check the other eigenvalue at all?
No.
No, we already know that this is non-defective. So that's how fast you can do that. Right, you can literally just do that right away. Okay, so that's number 20. 22, I'm probably gonna skip 22, it's the same kind of thing. It goes very quickly. On 22, well, maybe I should say one very fast thing about it. On 22, here's my matrix. What I wanted to ask you guys about, because this is a 5 by 5. There's the matrix, right? On 22. That is a 5 by 5. They did not give us the lambdas. So how are we supposed to get them here? Math?
It's just the main diagonal.
It's just the main diagonal, and why is that? Peanut? It's triangular. Yeah, exactly. This is a triangular matrix. So my lambdas are just 4, 4, 4, 0, and 0. Right, and now I can just check, okay, do they pull their weight or not? If I just check, so this is very, let's just do lambda equals 4 really quickly. If I subtract 4 off of the main diagonal, so that's going to give me this, subtracting 4 off of the main diagonal. I know I'm going kind of fast, but you can get the main idea here. A circle where the pivots are going to be, it's already pretty much in the row echelon form. How many free variables do I have there?
3. 1.
I only have one column, which is actually the first column, that does not have a pivot. So we get one free variable. Is that enough to pull its weight?
No.
Not at all, right? It came up here 3 times. 1, 2, 3. So, but it didn't pull its weight. So do we have to even bother with the other eigenvalue?
No.
No, as soon as one of the eigenvalues doesn't pull its weight, it's already defective. So we can do these pretty quickly, you see. We kind of get through that pretty quickly. Okay, with the remaining 5 minutes, I want to do problem 9 most likely, 7.2 number 9, unless there's a question about either of these. Number 9, I did it for my other class, and I think it would be good to do it. Okay, it's got some complex numbers in it. There's some good stuff to learn. Number 9, and then the rest of those I'll probably have to ask whoever put those on the board. Just have to do them in office hours. Let's look at number 9. So here it is, guys. We have the matrix A, which is 3, 0, 0, 2, 0, negative 4, and 1, 4, 0. And they're asking us to find all of the eigenspaces, the basis for all of the eigenspaces and whatnot. So this one, to really fully solve it, of course, we have to do the determinant where we subtract the lambda here, right? How am I gonna do this determinant?
Cofactor expansion, first row.
The first row is favorable to us, right? Because of the zeros that are there. So we could cofactor expand the first row. We have a 3 minus lambda. And then we have a little 2 by 2 submatrix. And you can do the determinant of the little submatrix. You're going to get lambda squared plus 16. Okay, and then what are my lambdas here? 3. 3 is one of them right here, right? And what are the other lambdas? Yeah, plus or minus 4i. Very good. Actually, let's stop right there. Do we already know if this matrix is defective or not defective?
So it's already non-defective. You have 3 distinct from.
There's no repeat lambdas, right? These are all different. There's no repeats here, so everybody's going to pull their weight, right? So we actually already know that this is non-defective. Really quick, let me talk about the lambda equals. So we have all 3 of these eigenspaces that we're supposed to calculate. Let me start off with 4i. I'm going to do the imaginary one first, if you don't mind. So for lambda equals 4i, of course, I have a null space I have to look at. We write down the matrix. We're going to subtract 4i from the main diagonal of A, right? Everything on the main diagonal gets 4i subtracted. So 3 minus 4i, 0, 0, 2, negative 4i, and negative 4, and then 1 and 4 and negative 4i. Okay, so I'm looking at a matrix that's a little messy because there's imaginary numbers in it, and it is 3 by 3. What do we know about that matrix that we automatically for sure can do? You remember what's one of the things that whenever you write down these null space matrices for the eigenspaces, you can always do something. Remember that the determinant was set equal to 0. That means that this matrix is not invertible, right? It's not invertible. So if we were to do EROs, which you guys are going to notice, I'm not going to do one single ERO to do this problem. But if I did an ERO, I know that a row would have to get zeroed out. So do you remember that now? You can always cross off a row. I'm curious if anybody wants to suggest a row. But I want to cross off row 1, row 2, or row 3, or it doesn't really matter, but I'm just curious if there might be a preferred choice here. The top one is actually one that I want to keep because it's so simple. right? So see the top row, let me write it down. The top row, if I think of X, Y, and Z here, the top row is actually telling me that, right? So the beautiful thing about the top row is that that allows me to say that X is 0. Right, the top row actually tells me that X is 0. So I'm gonna keep that row. Go ahead.
The middle row.
Sure, okay, we can cross off the middle row or the bottom row. I would say either one of the, I would choose either the second row or the third row to cross off. The first row is just so nice, I don't want to get rid of it because it's helpful. And now when I look at this bottom row, so here's my pivot. Right, my free variable is Z. So I'll call that T. And then if I just write down this bottom, so let's just write down this equation. This is X plus 4Y minus 5IZ equals 0. This is the equation that is aligned with the bottom row of the matrix. But remember that X is already 0. Kind of get rid of that. And if Z is a free variable and I call it T, we can go backwards now and solve for Y. We can actually cancel the 4s. So Y is actually going to be I times T. So between the X, the Y, and the Z, I can make my basis vector. To make the basis vector from the X, the Y, and the Z, what am I gonna do?
Plus one variables.
Bust out that T, right? We're gonna bust that T out of there. We have nothing there. We have an I there. We have a 1 there. Yeah, exactly. Yes.
Really quick, if you got the right lambda and you did EROs, you should get no free variables, right?
No, you should get free variables. That's what we got here.
Oh, yeah, never mind.
Yeah, you
That's
have to
not
get
a
free
lambda.
variables out of this.
Okay.
Oh, really quick, because I'm about out of time. If I took the -4i for lambda, do we have to do all of this work again, or can we write down the answer immediately?
It's a conjugate.
Right, we just take this one, right? You remember this? We just conjugate it. Conjugate it means that anything that has a real number on it just stays the same. And we just have to put minus signs on the imaginary parts. So the I just gets turned into minus I. You don't have to show your work for that. Okay, and then I'll let you guys do the other eigenvalues, lambda equals 3. See if you can work that out. If you get stuck, stop by my office later. I'll be glad to talk to you about that. But thank you very much for a great day today, guys. I appreciate it. Hopefully it made sense. And be safe out there. I'll see you again soon. Bye, everybody.